All right, let's talk about our next topic in the section of dry friction, and that is what we call slipping and tipping. So slipping and let's do lowercase tipping. It's nothing to do with going to a restaurant, all about dry friction. So let's say we have a box like this. Sitting on some surface that is rough, and let's say we start pushing on this box somewhere here, right? At some point, we'll assume that that box is going to move, right? How is it going to move? Well, if I think about a box like that, it's probably going to start slipping, right? And remember from dry friction, when we talked about the friction coefficient, once it starts moving, I'm going to need a lot less force, right? So the highest force I can apply here is going to be the one at impending motion. All right, so that's one case. Let's look at a different box. Let's say I tip my box on its side. It sits like this. Well, again, it sits on a rough surface, right? So it doesn't just slide. Now what happens if I put some force on there, if I start pushing on it, right? Not sure if anybody of you has to have moved a fridge before, but right, remember if you push at the very top of the fridge, at some point that fridge is not going to slide, it's just going to tip over, right? So we have the two things that can happen, right? We have, if my push against my box, right, it can start sliding, or it's going to start tipping, right? So in this case, it would tip around this point. Right, so what we're going to talk about in this section here is how do we decide if a box or any kind of object, in our case it's always boxes because it's nice and easy, how do we decide if it's going to slip or if it's going to tip? Right, those are the two things, two options that we have. And to look at that, let's create ourselves an example with a little more detail. Let's say we have a box. Again, boxes are nice and easy to draw. It has a weight of 200 kilonewton. It sits on a surface. Let's draw our surface on here. Right, sits on the surface here. The surface has a friction coefficient between the surface and the bottom of the box. We'll call that mu s equal to 0.5. What else do we need to know? We need to know we're going to put a force on here. The top corner, we'll say that force is P. We'll call this point right here, let's go back to black. We'll call that point, that's going to be our point A. We'll say that this distance, so the width of the box, is 4 meters. And we'll say the height of the box is 3 meters. Not a 3-4 triangle, but nonetheless. All right, so this is going to be our object. And we're now going to try and find out what happens if we put a force on that box. Basically, if we increase the force from 0 up to some value, is the box gonna slip, right? So move along, basically get it past impending motion, or is it gonna tip, right? So this happens before it slips, right? Very important. So we basically have the two cases, right? We have a case where we slip and a case where we tip. Now we already talked about the slipping, right? We know if we're gonna slip, that means that our box would be at impending motion, but maybe we'll do maybe we'll just write this down. Two scenarios. One would be slipping, or just slip. Two would be tip. So let's start with slipping. So let's do 1 and slipping. All right, for the slipping case, we know that this is going to happen, or it's going to start slipping right once it gets above the force that it needs for impending motion. So we can draw our free body diagram the following way. We can say this is our box right here. We know this box has a weight. It's given to us. All right, so we can say we have a weight. We're looking for the force, right? We want to basically find out what is the force that leads to slipping, I'm sorry. That'll be P. And then what else do we have? Well, we have, of course, a friction force. Now the box is moving, or the force is pushing it. It wants to move toward the right. So my friction force has to act towards the left. My friction force. And then, of course, the normal force is acting perpendicular to the surface. So with that, we have our free body diagram. And how many unknowns do we have? Well, we don't know P, we don't know N, and we don't know F. The only thing we do know is W. But of course, we know that we have an equation that we can write that connects F and N. All right, so maybe we'll just put that here. We know we're at impending motion. Well, we know at that point we get F is equal to mu s times N. And so now all we have to do is we figure out what N is. We'll get F, and from F we can get P. So that's relatively easy. Now if we want to get F, we'll need N. So if we want to have N, we can just do sum of forces in the y direction is equal to 0. That means we get minus W plus N. Doesn't get all that much easier. That means N is equal to W is equal to 200 kilonewton. That's my N. Then if I look in the horizontal direction, so Fx equals 0. What do we have there? I have P acting to the right, so positive, and minus F. I guess we should put our coordinate system here so we have our positive and negative directions all figured out. All right, so if I have that, then I can find what P is. Or maybe before we do that, maybe we'll just figure out what F is. Right, so we have F is mu times N. So that'd be P minus mu s times N equal to P minus mu s times, we'll just leave it as W for now. So that means I can get P is equal to mu s times W. Mu s was, what do we say? We said 0.5. So that'd be 0.5 times 200 kilonewton would be 100 kilonewton. Maybe we'll call this P slip so we can distinguish between the slip and the tip value that we calculated. All right, so that was our first scenario, right? That's the sliding one. So my box stays in full contact with the surface, but it starts sliding, right? That would be one motion. Now we said the other motion that we want to look at is that we tip, right? So for that we have to decide on what point it's going to tip about. For our boxes, that's always pretty easy to see, right? So it's going to tip around this point A. Now, if we wanted to just not be tipping, right? Because we want to have statics. Remember, as soon as it starts tipping or sliding, we move away from statics and we get into dynamics, which we're not covering here. So if we want it to not be moving, that means basically that, tipping, rotational movement, right? That's always a moment. So for our tipping one, we can basically say that the moment around A has to be equal to 0. So let's go, how do we have it here? So let's do 2 tipping. So 2 tipping. And again, we'll draw ourselves a free body diagram. So that will be our box right there. Our weight is still going to be acting the same way. And of course our force P is what we're looking for, so that's right there. Now the question is, what happens to our normal force and to our friction force? Let's put our point A here, right? Because that's what we want to tip about. Now let's think about this. Let's look at this picture, right? So if my box here would be starting to tip, right? It would be something like, if we were tipping, it would look something like this. All right? We're tipping about this point. Now if it's tipping about that point, this point would be the only point. This is where what we had point A, right? If we say this is the point, this is the only point that has contact with the surface, which means that the only place where our normal force can be acting is going to be at this corner here. Also, all the friction force has to be in that area. Now, if the only place that it can be acting is here, you know that the direction, right? The direction is perpendicular to the surface, so it's going to be straight up. So we know that in this case, what do we have in blue? We have our normal force is now all the way over here, and our friction force is there. Now, why is this important? Right? If we think back here, then we would say, well, if we want to do the moment around this corner right here, then N would have a moment arm, which means we have to figure out what N is and what F is, but we're not yet at, and we have to know where it acts. So it gets very difficult, but if we're tipping, then it's in the corner, doesn't have a moment arm, and we're good. So we can say sum of moments around point A is 0, right? That's the condition of just being not tipping. And what do we get? We get W. W is going counterclockwise, so it'll be positive. What's this distance? Well, we're assuming it's acting in the centroid, so it'd be 1/2 times whatever the length we said this box had was 4 meters. 1/2 times 4 meters, and then P, good, that's going clockwise, so minus P, and the height of that box was, what do we have, 3 meters. So P times 3 meters. Now if I want to find what P is, I'll have to solve for P, so I can say P is equal to, that would be W times 2 meter, 1/2 times 4, divided by 3 meters. So it'd be 2/3 times 200. 2/3 times 200 kilonewton, and that is 133 kilonewton, and that will be my P tip. All right, so now we have two values, right? We say slip is 100 and tip is 133. Let's go back to our picture here. Now again, let's assume we're starting at 0 with our force and slowly ramping it up, right? So I'm going to ramp it up. It's going to be 0, it's going to be 10, 20, 50. And as soon as I start reach 100, right, that was the value for slipping, my box is going to start slipping. Right, so I'll never get to 133 because my box is already slipping, and we said that once it starts slipping, right, then the dynamic friction coefficient is lower, so I'll need less force. So I don't actually get to the tipping point in this case. So we can say because P slip is less than P tip, we get slipping. Very simple, right? Because that's, if we got it the other way around, we'd get tipping. Now, what happens if I increase my my friction here. If this is a rougher surface, right? If this were mu s is equal to 0.5, let's do that real quick here. What would happen for mu s equal to 0.75? Let's go back into our equations here. Right? Doesn't change anything on our setup. Everything's going to stay the same. It's still going to be impending motion. The only thing that changes is this value right here. So if we pull this through, we can just recalculate what P slip is. Right? So if we do 0.75 instead of 0.5, so then we can say P slip would now be equal to 150 kilonewton. Does my P tip change in any way? No, right? Because there's no mu s in here or any connection there. So P tip equal to 133 kilonewton. Doesn't change. What does that mean? That means now, that's a weird looking W. Now we get tipping, right? Because now my P tip is less than P slip. Yeah, let's do it because it makes more sense here. Because P tip is less than P slip. Again, if we think about our little picture here, right? So if this box starts tipping before it stops sliding, then it's going to be tipped over, and then we'll have a whole new configuration to think about slipping, right? But this is basically the steps that we have to take, right? So whenever we want to analyze slipping or tipping, right, then we go in, we look at the two scenarios. The first one for slip, where we assume that the box stays in full contact with the surface, but we have impending motion. The second scenario is that our object tips, which means that's now only in contact at the very far corner here. And then we see what the moment is around point A, and that has to be equal to 0. All right, so that was slipping and tipping, but there's one more detail we should think about, and that is, we talked about already what happens on the slipping case if we start adding force, but we're not quite at impending motion yet, right? So we know that the force here is going to start creeping up as I go along, right? F is going to get bigger and bigger and bigger until it hits F max, which is N equal to mu S, right? And then it will start slipping. What happens if we think about the tipping case, right? So when I start the force here, or we said, or maybe we'll take our other, no, this is the right picture, right? So if we apply the force here, we said that at the moment, or just before it starts tipping, my normal force has moved all the way into the corner. But what really happens is that doesn't happen as a jump. As soon as I start applying a force here, that normal force is going to start slowly but surely, like as the force goes up, to move closer and closer until here, and then it tips. Right? So even if we're not at the stage of just about tipping, we can figure out how far away that normal force is acting. And of course, if there's no force, then it acts in the middle, because it's kind of representation of the entire interaction between the box and the surface. But let's have a look if we're applying a force to our box that doesn't quite get to tipping yet. So we do our box again. Here we go. We have our force acting up in the corner. Again, we're not at tipping yet. Close, but not quite there. You say our W, we say we have our point A, so we know what we're talking about in that corner. And now we said that our normal force is starting to move in this direction, right? So maybe it is now somewhere here. Of course, our friction force is still opposite to P, and we'll call this distance between A and the normal force, this little distance here, we will call D. And so then we can figure out what that distance is. We can say the sum of force, well, basically we can get N, and once we have N, we can do sum of moments, yes. So we can say sum of forces in the y direction is equal to 0, is equal to, now what do we get? We get, in the y direction, we get minus W plus N, right? Doesn't matter where it's acting, it's just somewhere there. That means N is equal to W is equal to 200 kilonewton, just like we had before, no changes there. Now let's do the sum of moments around A equal to 0. And that is equal to, let's see, now F goes through A, so it doesn't have a moment arm. P does not go through A, so that would be, and that's going clockwise, so minus P times, what do we say here? We have 3 meters, that was the height. 4 meters was the width, remember that. Times 3 meters. Then we have W. W is going counterclockwise, so plus W times 1/2 of the width, so we'll just say 2 meters. And then we'd have minus N, because it's going clockwise, times D. So now we can go ahead and solve that for D. All right, so basically we'd have to bring this one over so the stuff there stays the same. So we have, oh, we're not looking for N, we're looking for D. So D would be equal to, the signs here stay the same, will be W times 2 meters minus P times 3 meters divided by N. Now, what do we have there? That means equal to, so W we know was 200 meters. N is also equal to W, so that cancels out. And now P, I guess we have to set P. P would be 100 kilonewton, because that was the value that we had, right, for slipping, right? So let's say we are in the slipping case. Maybe I'll just do a P slip here. Let's make that a little more clear. Didn't say that before. Right, let's say we have the case where we're getting just about to slipping. Where would be our N, right? That's, I guess, the better, more precise question. So let's put slip. Let's do S. Doesn't fit otherwise. So what do we get then? We get W was 200 kilonewton times 2 meters minus P slip for our original case was 100 kilonewton minus 100 kilonewton times 3 meters divided by N, which was 200 kilonewton. That means we get 400, the kilonewtons cancel out, so that would be 400 meters minus 300 meters divided by 200. That's 100 divided by 200, 0.5 meters. All right, so we basically know that at impending motion, right, that's the slip case, we know that our N would have shifted its focus so that's half a meter from A. So remember, where's our full picture, right? If I don't put any force, it'll be here. It's at 2 meters, so at slipping, it'd be somewhere there, right? So that's all that I have for slipping and tipping. So maybe just a quick review, right? We said that we have two different modes of motion, right? We can slide along, we call that slipping. Or the other one is that we call tipping, right? Where basically we have a rotational movement. For the slipping one, we know that we can figure out when it starts to slip by assuming that it's at impending motion, where I get that my friction force is equal to the friction coefficient times the normal force. And for the rotational part, for the tipping part, we can say that we're going to assume that, or to have it not tip, we don't have to assume, it actually has to be the case that the moment around this tipping point has to be equal to 0. And from that we can do our analysis, and then whichever of those two forces is smaller, that's the motion that we're going to get.